Good afternoon. My name is Dennis Angeline. I'm a program manager on the Common Language Runtime team at Microsoft. I'm here to talk to you about the .NET framework and exactly how COM developers will perceive that framework. So I don't know about you guys, but I'm sensing quite a bit of excitement in the crowd. I've been at the overview talk this morning, at the talk later on this afternoon about the type system. And just the number of people that are showing up for the Common Language Runtime talks and the C# talk that was here before me. And then the quality of the questions that people are asking just really shows quite a bit of excitement in the crowd. So I don't know about you guys, but I can kind of feel that excitement. I know we're pumped up to talk about this stuff, and hopefully I think you guys are getting the same feeling. So if you went to that overview talk this morning, you probably got a pretty good idea of the features and functionality of the runtime. And you got a pretty good idea of how it's going to simplify development for people going forward. But if you're a COM developer and you're one of those COM heads out there that people like to call themselves, you might be scratching your head saying, well, gee, what does this new framework and this new common language runtime mean to me? Well, by far we've spent the last 3 years looking at COM development and looking at the process and really trying to understand where people would like us to make improvements and how we can simplify that process. And by far the biggest feature or the biggest aspect that COM developers will recognize when they move to this common language runtime or the .NET framework is the simplicity that it has to offer. So hopefully by the time we're done this talk, you'll get a pretty good feel for the framework and how it relates to COM. And you'll see that it's really an evolution of the work that Microsoft started, almost 10 years ago now, with the original release of COM. And at the same time, it's pretty revolutionary. It's a revolutionary way to solve business problems. So let's begin. We're going to start by taking a little walk back in history and look at the road that we traveled to get here to the .NET framework. We'll spend a good bit of time talking about the type system, because in my opinion, it's really critical for people to understand what we mean by type compatibility and a common type system. It's really one of the biggest things that differentiates us from the COM model, so we'll spend some time talking about that. And then we're going to dig into the productivity gains and the simplification that's made possible by that type system, along with a whole wealth of services that are available to you because you use these common types. So COM's a technology for building components. Components that can then be assembled and combined together to build rich applications, extensible applications, easily configured applications. But COM didn't start overnight. There were probably a lot of you out here in the audience that were around back in 1991, 92 when we first introduced Olay, which was Microsoft's technology for really embedding documents across Word and Excel. And we quickly realized that that whole framework or that whole set of technologies was something that we needed to make general purpose. And so in 1993, 1994, we introduced COM officially as a more general purpose mechanism for communicating across applications. And we've been enhancing that technology ever since. In 1996, we introduced ActiveX so that people could download code over the internet and execute COM components on the client. Later that year, we introduced DCOM so people could build distributed applications. And then in 1997, we introduced MTS to add transaction support. And earlier this year, we introduced, with the introduction of Windows 2000, we added COM Plus and the ability to do load balancing, queued components, and improved our transaction support. And throughout this history, there's been a number of common themes that have, traversed the whole spectrum of technologies there. One of those themes is the ability to be able to reuse code. Really back in those early days, COM was one of the first technologies that made it possible for you to reuse code across applications. And we did that largely through interfaces. So we defined an interface-based mechanism that let you implement an interface that can then be used across multiple applications. We've also had this notion of language neutrality. We've been language neutral from day one. And as long as you're an application or using a programming language that can understand interfaces and can implement interfaces, then it is perfectly viable for you to build COM components. And of course, all the Microsoft languages were very good at building COM components, but there are a number of other vendors that have built language extensions or made it possible to build COM components in their language. Also, the ability to have components and to be able to take these interfaces, combine them together, and build a component. And then to be able to take that component and sell it in a component marketplace so that other companies can be profitable from this technology. That's something that's been very important for us, that we build a technology that not only Microsoft could benefit from, but also the whole industry could leverage and become profitable as well. And we've also made it possible for you to preserve your investment in technology as we move forward. So we don't want to reinvent the wheel with every new technology that we introduce. We want to make it possible for you to continue to take the knowledge that you've gained or the knowledge that you've invested in over time, as well as the code, the code that you've written that uses earlier technologies. And I just want to reassure everybody that as we move forward into this .NET framework, and with all the cool new features that the .NET framework will bring to bear, we'll continue to preserve and advance those themes so that you'll be able to have language neutrality. You'll be able to continue to have a component marketplace where you build components and sell them and become profitable. And we'll continue to allow you to preserve your investment in technology. So the .NET framework, the Common Language Runtime, will help us to advance those themes that we started way back then. So I mentioned already that by far the most obvious or appealing feature for COM developers will be simplicity. And so we focused really hard on simplifying COM development. And we've done that largely by integrating this type system, which I'll talk about later. Which if you were at earlier talks today, you may have a pretty good feel for it already. By integrating this type system deeply into the compilers. Now, we didn't just bolt this type system on as an afterthought to the compilers. It's really integrated into the compilers natively, so that when you define a string, for example, in VB, it's a string that's defined by the common type system that the runtime exposes. This also helps us to reduce the learning curve, because now you're able to just learn your language, and at the same time you're able to build .NET components. You don't have to have any ramp-up time to learn COM in addition to your type system of your language. And this really enables us to eliminate much of the plumbing code, the code that people had to write over and over again. At the same time, we've introduced a number of powerful new features that would be especially of interest to developers. Things like implementation inheritance and the ability to be able to have application isolation so that when you install an application on a user's machine, you can be assured it's not going to be affected as other applications are installed down the road. The ability to have version resiliency and the ability to have this evidence-based security system. And we'll talk about some of those features as we move on. But there are other talks throughout the PDC here that if you're really interested in security or versionability, you probably want to check out those talks as well. So let me give you some examples of what I mean by productivity focused and eliminating redundant code, simplifying development. For example, IUnknown is something that, a lot of people are very familiar with and have implemented many times, and for the most part, it probably looks very similar, if not the same, every time you implement it. iDispatch, same thing. In the .NET runtime and the Common Language Runtime, we've eliminated the need for both of these interfaces. We've really taken those features and added them into the type system, added them into the Common Language Runtime so developers no longer have to implement those. So we've completely eliminated the need for those. Also, things like class factories, type information, connection points. These are all things that, with adequate information, we're able to implement on your behalf or provide implementations for on your behalf. We've also been able to simplify other tasks that developers do routinely, things like having to do reference counting. That's very error-prone, very tedious. Just something that would be nice if developers didn't have to do that. It would free them up from having to deal with a number of bugs and simplify the development task. Things like having to use query interface to be able to cast between types or to coerce from types. Having to update the registry or just write registration code, or even having the entry points that go along with the registration code. All these things just added complexity. And we've focused our efforts on eliminating and simplifying them. Dealing with H results and GUIDs, same thing. Having to convert from between different types like variants, beasters, and safe arrays. All these things added complexity, and we've worked hard to eliminate or simplify them. So how exactly do we do this? Well, what we found is that with actually, a minimal amount of information about the types that you're defining within your code, we're able to implement these things for you. If we know about the interfaces that your class implements, for example, we can do the type coercion for you, or without you having to use something like query interface. So we've introduced this new runtime type system. There was a talk earlier this morning that was devoted to the runtime type system. If you were at that talk, you probably have a pretty good feel for what's involved there. We've integrated it tightly into the compilers. It's open so that any compiler could use this type system. You've probably heard mention of 15 to 20 some odd compilers or vendors that we've worked with on implementing compilers that target the runtime. So it's open, integrated tightly into the type system, and it provides a rich set of base types. Way beyond just defining interfaces, we've added the ability to define classes and a rich set of base types that you can build and create more complex types out of. Because we have this common type representation, it's also easier to transfer data back and forth between languages. So I use the example of a string. In the past you've had to deal with beasters and char stars and Unicode strings, and you had all these different variations of strings. In this new model, the type system defines one string type, and it's usable across all those languages. So we get much better data transfer and cross-language interoperability. We've also have a common way of not only using those base types, but defining new types. So the whole mechanism for defining, managing, and using types, user-defined types, is described by this type system. So when a compiler encounters a type definition, it can use the type system to emit this type information, or metadata as we call it, to the binary, and it's written in a format that's understandable and can be used by other languages, other compilers, other tools, and by the runtime. Now, one other big thing is that we use this type system not just for exposing our public objects or objects that you would want to expose out to other applications, but you also use the type system for defining internal types. So the types that you're just using within your application are also defined using the common type system. So we have all types being used everywhere using the common type system. So let me just tell you about a few interesting improvements that we've made in this type system that you would have missed in COM, in type libraries, for example. So the most obvious is that we've introduced classes and the ability to be able to support classes. So you don't have to always use interfaces anymore. Now that doesn't mean that we don't recommend interfaces. By all means, interfaces have their place and are certainly more appropriate in for a large set of problems. Anytime you have classes of functionality or sets of functionality that you want to expose out publicly, and you expect to be implemented by multiple or have multiple implementations of, an interface is more appropriate. Now that doesn't mean that they're something that you want to use all over the place. As I already mentioned, the type system is used for internal types as well as external types. So it's very important to be able to expose classes when you're dealing with internal types, as well as interfaces. So the classes that we have methods, properties, as you would expect. They also have fields and events. The fields are directly accessible, and the events are first-class members, just like methods and properties. So you can actually go up to an object and look at the events that it sources. These classes have constructors, parameterized constructors, a welcome addition for COM developers. So now when you're constructing the type, you can actually pass arguments to the constructor and have the object created in a particular way. We support method overloading, so you can have multiple methods with the same signature. And we bind based on the complete signature of the method. We'll talk more about that. You can have static instance and virtual methods. You can control the accessibility of the methods. Some methods may be public or private or only accessible within the assembly or within the family. We'll talk more about assemblies later. And as I already mentioned, we support implementation inheritance. Another interesting concept that we have in the type system is the idea of value types. What value types are stack-based values that just take up X number of bytes on the stack until they're actually treated as objects, at which time they can have object semantics. These are highly efficient objects. These are things you might use if you want to create a point type, for example. Very efficient. You just want to access the X and Y properties, but sometimes you want to be able to treat it as an object and stuff it into a collection. So a very efficient way of creating value types. So let me talk just a bit about implementation inheritance. So we do support implementation inheritance across languages. I'll show you a quick demo of that in a little while. You can extend at most one base class, but you can implement multiple interfaces. So we have single inheritance, but multiple interface implementations. This gives you the ability to have binary libraries that are reusable. So they can be used by any language and extended by any language. This is a pretty key idea here. That means that you can create a library like the frameworks that we've created, and it can then be consumed or used by VB, by C#, by C++ clients, by COBOL clients, or any of the other compilers that target the runtime. So it's pretty powerful. It's not like you have data types that you're using just exclusively in VB, or data types that are for exclusive use of C++ clients or Java clients. They're not language specific. They can be consumed by any language. And we don't go through any tricks to make them consumable by any language. They're just natively understood by those languages. So examples, obviously we have this entire .NET framework. That's a library of types that you can use and extend and build on. We have windowing classes and types for doing web forms and data access, a whole slew of other types. As well, we would expect third parties, people like yourself, to go out and build additional libraries that have other specialized features and functionality, and market those libraries and become profitable in that way. Also, corporations will also find it very useful to be able to create libraries of their own with their own specific business logic built in. So let me just compare this type system that we've been talking about for a minute to the COM standard that we're all familiar with. So in COM, we have multiple language type systems today. So if you're in C++, you're used to dealing with char stars and the like. You're used to building an application, compiling it with your C++ compiler that then relies, maybe heavily on ATL or on MFC. Probably certainly relies on the C runtime, MSVCRT. If you've used VB in the past, you're used to dealing with beasters and the types that are familiar to VB programmers. And you're probably more or less aware that there's a VB runtime underneath you that's actually making all that happen. And if you use Java, you're used to Java types, and you had the Java VM to construct your types with. But with the COM binary standard, we were able to create types in any language that were binary compatible. And as long as your language could understand interfaces and deal with vtables, the objects could interoperate with one another at the binary level, even though the runtimes that they were using underneath were not type compatible. We were compatible at the binary level. So this was a pretty cool idea. It was a great concept. At the time, it was probably one of the only mechanisms that provided language neutrality. That's essentially what we got out of having a binary standard like that. You could implement COM components using any language. But in a way, it was really a secondary type system. It was kind of a slimmed down type system. It wasn't that rich. It was limited to interfaces, and the data types that you could use were somewhat limited. But it was a type system in effect. And the problem was that it's different from the type system that you use in your language. It's not the C++ type system. It's the COM type system. And it's not the VB type system. It's the COM type system. And so that required us to go through an additional learning curve, or made the learning curve even steeper, because we had to learn not only the type system that we were familiar with programming in, but also the COM type system, or the COM binary standard. And it also made it necessary for us to often translate data from one type system to another. So anybody that's dealt with beasters from C++ and has had to call sysalloc string to allocate a beaster, and then so you can pass it to a VB object, is familiar with that. In the new type system, the runtime type system, we create types that are objects that are type compatible. So all the compilers, the C# compiler, the VB compiler, the C++ compiler, the COBOL compiler, and all the other compilers that you've seen over the past few days, all use this common runtime type system for defining, managing, and using the types within their language. And what we get as a result when you compile your application are type compatible components that are able to interoperate on a through a type mechanism rather than through just a binary mechanism. So we have type compatible as opposed to binary compatible. Now, because we have that information within these objects, because they use this common type system, not only do we get smooth interoperability or cross-language integration, we also are able to provide a number of added values or added services on behalf of your object. So I mentioned type coercion already, things like activation, error handling. We're able to offload a lot of that work for you. So you may be wondering, so what about all my objects that are using this COM binary standard? If I move to this new type system standard, what happens to them? Well, one of the services that we provide, because we have that type information, is the ability to be able to do interop between the binary standard and the type system standard. And so if you have a COM object today that implements a number of interfaces, you're able to import that object into the managed environment and treat that object just like any other managed object. You truly treat it exactly like a managed object. You knew the object, you coerce between types by casting, and so on. Likewise, if you have a managed object that you built using the .NET framework, and uses the runtime type system, we're able to take those objects and expose them out as binary compatible objects to COM clients. And so we get very smooth interoperability between these two standards. Now, that's not really what this talk is about. That is a whole separate talk in and of itself. And if you're interested in that talk, you can come tomorrow at 2:30. This is a cheap advertisement for my talk tomorrow. But you can come tomorrow at 2:30 to another talk, and we'll talk exclusively about interoperability. But I'd rather hold off on those topics for now, if you don't mind. So let's dig into some details about simplifying development. Really, the simplifications all boil around self-describing objects, or center around self-describing objects, object management, and the versioning support that we have. So let me dig into these. So first off, all the types and all the objects that you create with the runtime type system are self-describing. They're described in what we call metadata. The metadata is the representation, or the persisted representation of the types that you define in the type system. It's stored along with the executable. So whether it's an exe or a DLL that you're producing, the metadata is in there, in the executable all the time. It's not optional. If you don't have metadata, you don't have a type. So it's always required. It's always there. It's defined and emitted by the compilers directly from your source code. So there's no need to have any separate IDL file, no need to have any separate type libraries. The compilers look at your source and emit the type definitions directly to the binary that they produce. It's also extensible through attributes. So we've baked as much stuff into that metadata that we think we need, but there's also others, compilers or other applications that would like to put additional information in that metadata. And so we've made it possible for you to put attributes on your types, or in fact, you can put attributes on anything, whether it be a type or an interface, a parameter, a property. You can attribute these entities, and the attributes are persisted in the metadata along with the rest of the metadata. You've probably seen examples of these attributes in demos over the last few days. The web method attribute, for example, is one of the attributes that you've seen in the ASP Plus demos we were doing the other day. But you can create your own attributes and extend and have your own metadata emitted by the compilers. Another key difference here between COM is that these binaries then become the single source of type information. So they really consolidate header files and IDL files and type libs. We've had various sources of type information in the past. So this is the single consolidated source of type information. It'll be used by everybody. It's used by compilers, obviously, when they need type definitions for other types that may have been defined elsewhere. It's used extensively by other tools, profilers, and the like. And it's also used extensively by the runtime itself, by the runtime execution system. So the metadata, let's take a quick look at what it actually contains. It's very rich, much richer than the information you may be familiar with in type libraries. It contains the identity, first off, along with type definitions and type references. The type references are really what differentiate us from the COM model of type references. So let me talk about the identity first. I should have added on here, it contains the name of the assembly. We'll talk about assemblies in just a minute, but the assembly is given a name. It also contains the version, the culture, and the publisher information along with that name. So it's a 4-part version number. You can explicitly identify the version of the metadata that you're emitting. The culture allows you to say that this is U.S. English or French Canadian or whatever the culture may be, if there's cultural specific information in the metadata. And it can also contain the identity of the publisher in the form of a digital signature. We'll talk more about that in a minute. The metadata also contains type definitions. I mentioned earlier that these are both the internal and the external type definitions that you use. So they're the types that you're exposing publicly as well as the types that you're using internally. It includes the definitions of the classes and interfaces and structs and enums and everything else that you may be defining, along with the methods and properties and fields and events that those types have. The type references are pretty different in that they define or they capture, along with the type reference, the version of the type that it's referencing and actually how to locate that type. So we actually capture the version information of the dependent type in the assembly that you're building. So as you're going through compiling a type, when you reference another type, during the compilation process, that version information will be embedded into the binary that's generated. This lets us track down version dependencies down the road and really be able to build a hierarchy of dependencies by looking at any given type. We can look at one type and see all the types that it depends on. The framework also provides a mechanism called reflection for doing dynamic inspection of objects, or actually reflecting on objects. So through these reflection classes that are exposed through the framework, you're able to access this metadata just like the compiler or the execution engine would. You have access to all the types that are, and all the information that's emitted in the metadata. You can inspect the types, the methods, the parameters, the return values. You can actually use this mechanism for creating instances of objects, much like you would in COM through an iDispatch. So you can create instances, invoke members, invoke methods, properties, and actually sync or source the events through reflection. And there's no additional work that's needed by the class author. So you simply author your class, and because the metadata is emitted by the compiler, the reflection mechanism is able to then look at that metadata and make it available to anybody. So there's no need to implement iDispatch or produce a type library or anything like that. There's also another handy mechanism called reflection emit that I just wanted to throw out here. Reflection emit, rather than allowing you to inspect the types, it allows you to emit the definitions of new types. So using reflection emit, you can actually define a new type, create some methods, add the methods to the type, and actually bake the type, instantiate the type, persist it to disk, and do all that through this reflection emit class. So let's talk a bit about assemblies. Assemblies are the unit of packaging, a unit of deployment, and a unit of versioning. When you create a collection of types, you pull them together into an assembly, package them, deploy them, and version them as a unit. The version is assigned to the assembly. The version number that I've been alluding to is the version number for the assembly. And types are uniquely identified by the assembly that they belong in. So you'll never reference the foo type alone. You'll always reference the foo type in such and such an assembly. Now, because the assemblies contain the publisher identity and can be signed with the publisher's digital signature, we're able to uniquely identify types when they're signed in that way. So you can identify a type foo in this assembly that's signed with this particular publisher's key. What that does is it allows us to provide name uniqueness, first off. So while the type name itself is not unique, the type name in that assembly signed by that publisher certainly is unique. And so we're able to get type uniqueness or name uniqueness that way. It also allows us to securely bind to those types. So when we're actually doing the binding, when a user of a particular type references another type, in the process of actually loading that other assembly, we do the check of the publisher's public key to make sure that it actually is indeed the assembly that the caller thinks it is. This makes it impossible for somebody to, for example, take an assembly written by Microsoft and replace that assembly on someone's hard drive with another assembly that has all the same types but does something malicious. If you tried to do that, in the process of loading that assembly, the publisher's key in there, in that assembly, would not be the correct key. It would not be Microsoft's key, and so the binding would fail. And it also gives us a way of protecting a namespace. So it prevents other people from adding types with the name, with a particular name, or adding types to a particular namespace that already exists. Another cool feature is the ability to be able to have application isolation. In other words, to be able to install a type or install an assembly on a user's machine and be assured that it's not going to affect other applications that exist on that machine. And more importantly, be assured that it's not going to be affected by other applications that may be installed subsequently on the user's machine or removed from the user's machine. So these assemblies that I've been referring to can come in two forms. They can either be private assemblies or shared assemblies. Private assemblies are assemblies that typically are not signed by a publisher and are installed on a user's machine simply by copying them to a particular directory. So there's no need to register any of these types in those assemblies if you want to simply have a private assembly. Installation can be as simple as just X-copying a handful of DLLs and an executable to a user's machine. No reason to touch the registry, no need to update the registry or do anything like that. Those types that are installed in that fashion as a private assembly are only accessible to that application, so they can't be used by other applications. And therefore, you can't have other applications coming out, being installed and replacing those assemblies. Another alternative is to have shared code installed in what we call the global assembly store. And so you can use APIs for actually, during the installation process, putting code in this global assembly store. In order to go into Global Assembly Store, it must be strongly named. It must be signed by its publisher. And that gives us that name uniqueness again. And because it has the name uniqueness, we're then able to share that assembly across multiple applications. I mentioned that along with the name, we have the version information. So in the course of putting something in this Global Assembly Store, you may be updating or adding another version of a particular assembly. So you can have multiple versions of the same assembly in a global assembly store. And that makes it possible then to have two applications that both use the same types in the same assembly, but different versions of those types. And so you can have two applications that are using different versions of MS-ADO, for example, at the same time installed on the user's machine. Again, this eliminates, because we have this X-copy deployment mechanism, it eliminates the registration problem, eliminates the need to have DLL entry points for doing registration, eliminates the need to have to write registration code. It also eliminates the DLL hell problem that everybody's familiar with, where one user replaces another user's DLL. And it makes possible this Xcopy deployment story that I just talked about. So let's take a quick look at how some of this actually works. So what I have here is a class simply called A. I wanted to keep this very simple so we can just focus on the details here. A class called A that has a method X and a method Y, and it's written in C#. And this is all there is to the class. You'll notice up top here I say using system. What that does is it allows me to reference the console type, which is part of the frameworks, part of the .NET frameworks. And the console just has a write line method, and all I'm going to do here is display that method A, method X, and method Y were called. So I can actually build this. And then I'm going to run a tool called ILDASM. Oops. Sorry. On that DLL. And I'm going to make the font a little bigger so you can see it here. And if you look in here, you can see the metadata that I've been talking about. You can see I have a DLL called A in a namespace called C# code. And if you look back here, you see C# code is the namespace that I created. The type is called A. It has a constructor. The class is public. It has a method called X, a method called Y. And it tells me the type that are actually being passed as arguments to this particular method. I can also look in the manifest here. And the manifest is a part of the assembly that contains the information about the external references that that assembly has. So if I look here, I can see that this particular assembly references another assembly called MSCoreLib. That is the .NET Framework assembly. You can also see that I have the originator key here for that assembly. I have some hash information, and I have the version number that it was built with. So I can tell that this particular A.dll is built with version 2014 build 1812.10. And so that's the information that's actually emitted by the compiler. Now let me go back here and bring up some more code, some VB code. And if you look at this VB code here, I'm actually importing the namespace C#. Now I should just stop here and clarify. Namespace is just a way of identifying a type, the name of a particular type. It really doesn't have anything to do with the binding or the resolution of types. It's not used in the lookup of types in any way. The types are looked up and resolved strictly by the assembly name. But within the assembly, the namespace becomes a part of the type name itself. So I have a class here called class B, and it inherits from class A. So you can see I'm using inheritance across languages here. I add another method Y that takes 2 integer arguments. The base class took 1. And I use the overloads keyword in VB. And I have a method Z here as well that I added to the type. So I can build this bugger in VB. And notice when I build it, I'm actually using a couple of command line options here. I use /t:/library. That basically just tells it to build a DLL. And I use /r:/a.dll. Now, /r is a reference, and it says in the process of compiling this type, I'm going to reference the types in A. And so I pull in those references that are found in A. And the compiler actually then goes out and looks at the metadata in A and is able to get the definition of the base class A. So then if I use ILDASM again, and by the way, ILDASM stands for IL disassembler. IL is the intermediate language that the runtime uses. And if I look at this manifest in here, I can see that I have now a dependency here on the external assembly called A. And I didn't include any version information, so the version is just 0 here. I could include the version information during the compilation process, in which case it would have the version information there. So let me point out a few things here that we did. So first off, in looking at these, a couple of things to note. First off, I'm using a type across languages, right? I have the type A written in C#, and I'm using it from the type B. It's the base class of B. There's no I unknown implementation here. There's no GUIDs. There's no class factories. There's no type libraries, and there's no separate IDLE file. So just in a few lines of code that I've demonstrated here, there's just a whole wealth of simplification that's gone on. To do that in the past, there would have been type libraries, class factories. We would have had to implement I unknown. We may have had to implement iDispatch if we wanted to use it from VB. But all that's been eliminated here. So I'll come back to that in just a minute, and we'll actually use those types in another demo. But let me talk about a few more things. So the whole activation process has been simplified as well. In COM, you activate classes through a class factory. And if you think about it, the reason you had a class factory was because the only one that really knew how to create an instance of a particular type was the object itself, right? Externally, there was no way to look at the DLL and know the types that were in there, or you could know types that were in there, but you couldn't instantiate those types externally. In fact, you didn't know the language that the DLL was written in, so you couldn't possibly have instantiated those types externally. But now, because we have that metadata, the runtime is able to instantiate or activate these types on your behalf. And so you do that simply by using the new operator in your language, or whatever the appropriate mechanism is for instantiating language types. So it uses familiar language syntax, and you're able to pass constructor arguments. Eliminates the need for class factories, eliminates the need for co-create instance, eliminates the need for DLL entry points, and also for the registration code. Type coercion. We're able to coerce from one type to another, again, because of the metadata we have. We know the interfaces that are implemented by a particular type. We know what its base classes are. And so we're able to cast from one type to another simply by using a cast operator. And you use whatever syntax is appropriate in your language, typically just a cast or an assignment. And there's no need to call query interface, no need to actually call into the object to make the type coercion happen. Error handling is also done quite a bit simpler. In the past, we've had H results. We've had to deal with defining new H results. We've also, so that all methods could return H results, we had to deal with out-ret-val parameters. In the runtime, we have a exception handling model that allows us to propagate exceptions across languages. And so you can raise an exception in one language and then catch the exception in another language. And the exception just flows along with the call. So we can propagate these exceptions between languages, and we can also propagate them out to unmanaged code. So you can so you may call out to some unmanaged code where an exception happens, and we're able to propagate that exception back into the managed code. Or you may even have a scenario where where you call from managed code to unmanaged code back into managed code. And we're able to flow that exception through the unmanaged code back into the managed code. We don't impose any particular syntax on your language for dealing with these exceptions. So in C++, it's a try-catch. In VB, they've added some new syntax for dealing with exceptions, but you can still use an on error if you wanted to. And we have a number of exception classes that we've created for you to use. Things like file not found exception, out of memory exception, that sort of thing. But you can also create your own exception classes for more specific exceptions. So another thing that we've done to really simplify development and really reduce the number of errors and problems that people have had is taken a responsibility for the lifetime of managed objects. So objects references are always traced. as objects are used, the references that other pieces of code hold on those objects are traced. And so we're able to know at any given time how an object's being used and who's referencing it. Those traces are, move across languages, so you can have references to objects from different languages. And an object is simply freed when there's no longer any references held on that particular object. This allows us to eliminate cycles. So in the past, you've had problems with reference counting where one object is holding a reference to another object, and that object's holding a reference to the original. So you've had cycle problems with not knowing who to release first. And then all the other problems associated with reference counting and leaks that are caused by that. In the process of managing these objects' lifetime, we also compact the heap. So all these objects are allocated out of a heap that the runtime manages, and the objects are compacted as we do the collection process. Actually, not every collection involves a compaction, but periodically a compaction may happen. And in doing this, we're able to greatly reduce the working set used by applications because we compact this heap so that the larger, longer-lived objects tend to be compacted in a central place within the heap. And these other smaller, shorter-lived objects tend to live out in the heap. We're able to get much better CPU cache line performance and much better working set performance, or a smaller working set, by doing that. So let me go back over here to this demo quickly and show you a third piece of code here. So now I have some C++ code that's actually referencing the type B and the type A. So B is the thing that's written in VB, and A is the thing that's written in C#. And so to create this particular type, I just activate it with a new in C++. I just say B equals new B. I call method X, Y, and Z. And then I'm going to coerce this down to a type A and call method X and Y again. So notice up here I add a reference to, I just say using these particular namespaces. And this is just really a shorthand for referencing these particular types. If I didn't say using namespace VB code here, then I would have had to qualify the type B as VBcode.B. And likewise, if I didn't use the C# namespace, I would have had to qualify the type A as C# code .A. I also, one thing that C++ does a little bit differently here is I import the definitions of these types in source code. So I actually use a #using statement here to import the definition of A and B during the compilation process. I showed you earlier how the C# compiler and VB compiler actually do that on the command line with that /R parameter. C++ is a bit different in that it does it by importing the types in source code. So I'll build C, and I get c.exe, and if I run that, you can see that I'm calling method X on class A, method Y on class B, and then method Y on the base class, and then also calling method Z on class B, and method X and Y on the base class again. So I'm calling between languages from C++ to VB to C#. And I've activated the objects simply by doing a new. No class factories, no need to call create instance, none of that. So let me go back here to the C# code and add some code in here. I'm just going to do a validation of one of the arguments, make sure the date that's being passed to me isn't empty. And if it is, I'm going to throw an argument exception. And I'll go back here to the C++ code and add a call to that date method. And let me just take out the catch block for now. And let's actually build it this way. And then run C. Oops. Oops. Oh, sorry. So you can see what happens now is a dialog pops up to actually fire up the debugger. It gives me a choice of debuggers, and so I can pick which debugger I want to use right now and actually go into launching the debugger and debugging the application. I'm going to say no here, and we can just see that the exception is then just dumped to the console along with the call stack. So we can see I was calling main and then module X, and then an argument exception happened. So I can come up here and back to C. And put the try catch block in there. And rebuild that. And now you see I caught the exception, and I'm just dumping out exception caught and then the call stack myself. So it's similar to what the runtime does if it catches the exception. But it's just an example of being able to propagate those exceptions across languages from VB to C++. So let me talk a bit about the binding that we do. And if we have time, I'll do one more quick little demo. So we bind methods dynamically at runtime. When we're actually calling that method X or method Y there, at runtime, the method is actually being bound to the caller based on the method name and the complete signature of the method. And this gives us the ability to be able to have method overloading. So the first time that method is called, we actually, during the process of JITting the particular method, we actually do a lookup and actually locate that particular method. After that first call, though, the call is simply just the overhead of doing a jump to that particular method. So what you end up with here is a very resilient binding mechanism because you're able to evolve types over time. And you can add methods or remove methods to your base class over time. And you get this performance of early binding with the resilience of late binding. Right? People have used iDispatch in the past for the resilience, the ability to be able to call a method and change the methods that I'm calling and have them bound dynamically at runtime. But it wasn't performant, right? And they used late binding for higher performance applications, but they didn't get that version resiliency because they were bound to a fixed vtable layout. And when you called a particular method, you basically just jumped to a particular offset in a vtable. With this new mechanism, we kind of get the best of both worlds. We get the performance of early binding with that version resiliency that we like out of late binding. So this allows method overloading and allows the types to evolve over time without having to implement iDispatch or anything like that, and without a fixed vtable layout. So I mentioned the assemblies earlier. The assemblies are also a unit of versioning. I mentioned that we can have multiple assemblies of different or the same assembly with different versions installed on the machine at the same time. It's also configurable by an administrator, how the binding actually happens. So an administrator can set the configuration policy for a particular application to say that it should use the version that it was actually built with always, or it should use a particular version, or it should use a current version or a version that's greater than such and such. So that binding policy is configurable at runtime. And the binding policy is enforced by the runtime because we're actually using that information that's baked into the assembly when it was compiled. Another mechanism that COM developers will welcome is the introduction of delegate-based events. If you're in the talk earlier on C++ or C#, you see just how easy it is to use delegate-based events. Events are built into the type system. They're first-class members, much like methods and properties, and so you can look at a class and actually see the methods that are on that class, and see the events that are on that class. They're strongly typed, so you can have a method that takes certain arguments and is of a certain type. And they're tightly coupled events, so that the caller has to know about the sync of the event, or the person handling the event has to know the type of the thing sourcing the event. They're very cleanly integrated into the languages. So C#, for example, allows you to add an event handler using a plus equals operator. So you can just take the event on a particular class and say plus equals and add your delegate to that event in order to be notified when the event is fired. So it's a very simple user model, much different than the connection point model that people are used to dealing with in COM. So let me just run over here and do one more thing before I move on to security, if we can switch over to this monitor again. So I wanted to just show you the binding, because it's something that's pretty cool as well, an example of this dynamic binding. So I'll add another method here. Let's just call it method W, and I won't put any arguments on there. And I'll save this. And I'll just rebuild A. Okay, so now I haven't built the client. I haven't built C. And if this was a COM application, we'd be wreaking havoc when we run this thing. We would expect things to blow up because interfaces would not line up anymore. And so when I run C now, we'll see that actually everything works just the way it worked before, because the binding happened dynamically at runtime. Now the exception is caused by the exception that we created earlier. But in fact, I could add a whole bunch of methods to this class, and the binding would happen dynamically at runtime. It would actually look up the methods X and the method Y with the appropriate signatures and bind to the appropriate methods, even though the layout of the base class has changed. Thanks. So let me just, you're probably wondering, so what happens if I delete this method that is being called? So let me do that and build A. And we're not going to make any magic happen here. But if I cancel out of the debugger here, you'll at least see that we throw what's called a missing method exception, which is much easier to deal with than just jumping off into nowhere and causing an AV. So let me just jump back here quickly. We don't have a whole lot of time to talk about security or the new evidence-based security system, but I really think it's one of the just coolest new features of the runtime. So you probably would, if you're interested in security at all, you definitely want to check out the security talks that we have coming up here. But the basis of this new model is that it's an evidence-based system, and code can provide evidence in the form of a zone, a publisher, an application, an assembly, or even other types of evidence that you may come up with. And so associated with any chunk of code is the evidence that goes along with that code. And then in order to access certain resources, certain permissions are needed. So in order to access files, for example, or a file system, you may need file access permissions. And the runtime security system is able to take the evidence that's produced by the code and look at the permissions that are required in order to execute or access a particular resource, and make a decision as to whether that particular code should execute or not, based on the evidence that it's gathered. Now, in the process of doing that, we walk all the way up the call stack when it's appropriate. So not only does the caller have to have the proper evidence, but all the frames on the call stack have to have that evidence as well. So it enables you to prohibit code from being misused in a particular way. So, for example, you may have some code written by, say, Intuit or Sheridan or Farpoint that does something that they only want to be able to use, they only want to be able to be callable from other code that's been authored by Sheridan or Farpoint or whoever the author is. And so the code can actually have permission checks in it to say that in order to execute this, you need certain permissions, and those permissions would only be granted to code that came from that certain particular publisher. Likewise, you could say this particular method can only be executed by code that's a part of this application or this assembly, or code that came from this particular zone. So what this allows us to do is really have a semi-trusted mode of execution. If you think about the AuthentiCode model that COM has, it was really an either-or model, and it's contrasted with the Java model all the time, where people are able to download code, and with AuthentiCode, they make the decision at download time. Do I trust it or don't I? Once they make that decision, the code is installed on their machine if they say yes, and then the code basically has free reign of any resources that are available on the machine. With this model, we're able to download code and look at the evidence that's provided for that code and actually make trust decisions based on that evidence. So we may be able to say, code that was downloaded from the internet zone, I only want to grant access to a particular scratch area on my hard drive. I don't want it to be able to write anywhere. Or I don't want it to be able to use my printer, or so on. So you can really control access to resources based on the evidence that's provided by the code. One form of evidence that we also have is type safety as well. So we're able to look at code before we execute it and determine if it's verifiably type safe. So in our IL instruction set, and by looking at the metadata, we're able to determine if this code is actually type safe, if it's being used in the way it was intended to be used. And then that could go into making that decision on access to resources. So you may say that only code that's verifiably type safe is allowed to do these particular things on my machine. And so we're able to have much more reliable code. Type safety ensures that we're only doing operations that are legal and appropriate and intended to be used. And it prohibits us from doing things like over-indexing arrays and doing invalid casts from one type to another, that sort of thing. So it's perfectly legal to have type unsafe code in the runtime. If you're in the C# talk earlier, you saw Anders talking about the unsafe mode in C#. It just won't be verifiably type safe, and it will require additional permissions in order to be able to execute that code. But it's just added information that can go into that decision that you make to determine which resources you're granting access to. So in summary, I'd like you to leave remembering that this common type system is really critical. It's a type system that we've made open and available to a number of other compilers, and it's the key to simplifying the development process. It's the key to solving many of the problems that COM developers have encountered in the It allows us to eliminate things like IUnknown and IDispatch and type labs, class factories, GUIDs, that sort of thing. And it also allows us to add cool new language features and things like inheritance and VB, and be able to do automatic activation and manage object lifetime and provide this evidence-based security system. There's some interesting talks that you should try to catch if you're interested in performance considerations. There's a talk coming up. I'm not exactly sure when these talks are, but these are the numbers along with the titles. There's a talk on performance considerations. I'll be doing another talk tomorrow at 2:30. That talk's called Interoperating or Using Existing Code from the .NET Framework, where I'll talk specifically about how to use managed code and COM types or DLLs that expose static entry points interchangeably. There's a talk dealing specifically with transactions and COM+ services. Another talk about deployment and versioning of your .NET application. I think that talk happened this afternoon, so that may be behind us. There's two talks about security, and then there's another talk that really digs into the details called How Does Hello World Really Work? So install those bits and go out there and enjoy it. I think you'll find developing applications with the .NET framework much easier than you've had in the past with COM development. So enjoy it. Thanks. So we have some time for questions here. Yeah.
Yes, hello. When you used the ILDISM tool, it was very nice, but it also exposed a lot of the structure of my application. It also exposed a lot of the structure of my application. What if I don't want to expose this structure in this way? Is it possible?
Yeah. That's a good question. We are aware of that issue, and we're actively trying to work with third parties to come up with a mechanism to do obfuscation so that we can obfuscate that information that's in that metadata. We're unclear whether we'll have that by the time we release the product or not, at least in the first release.
So this is currently an issue?
It's something we're aware of and we're actively working on. Yeah.
Okay. From the way I understand it is if you don't have metadata, currently the runtime system won't allow you to run or cannot support you. And if you have metadata, then you expose the structure of your application.
Yeah, it's not exactly that. You'll have to have metadata. The question is whether or not the metadata will be decipherable by other things, inappropriate for people that are just kind of browsing around and want to look at the layout of your types.
Okay, thank you.
The layout of the types isn't that important. It's actually the IL instructions within there that are, more interesting when it comes to protecting.
It's the algorithms, but still it gives a good idea.
Yeah.
Thank you.
Thanks. Yeah.
I assume that an application may contain assemblies and COM components, old COM components. Is it correct?
An application can contain assemblies and it can contain wrappers for COM components.
And what happens in this situation with isolation?
I'm sorry, what was that?
You talked about application isolation. What will happen with COM components which are wrapped in this application?
So the COM components will be installed along with the application in the usual way, or if the COM components are already installed on the user's machine, the COM components are there. What you'll have to install with your application, though, is a very thin wrapper that just includes metadata that describes those types.
But that means that for COM components, we continue to have the same behavior. That means only one version, no multiple versions, and so on.
If you want to rewrite that COM component on managed code, you can do away with all those restrictions. But as a COM component, you're going to have to live with the restrictions that are associated with that. So I'd really like to not talk about COM interop problems at this talk. We can spend a whole hour on that tomorrow. So if there are interop questions, if we can hold those till tomorrow.
Also questions about COM plus events and object pooling and so on will be the subject of other presentations.
Yeah, sure.
Will you talk tomorrow about it, or this is the other presentation about services and transactions?
No, there's another talk tomorrow as well. I won't be talking, but there's another talk specifically about transaction and COM plus services tomorrow.
Okay, thank you.
Okay. Yeah.
Before I ask my question, what is a good source for little random questions that I have? I mean, I have 900 questions. I'm not going to ask them all right now.
So there will be news groups set up, public news groups. There's a public news group as well as a news group just for PDC attendees that are set up already or will be set up. And I'm sure you'll get information through the PDC coordinators. So that's where you should direct your questions.
Okay. The big question is, I'm not going to ask about COM interop, but is the .NET completely replacing COM in the sense that the end goal is that no COM components will ever be used?
No, we don't really look at it that way. We're providing another mechanism for you to build components that are that simplifies the development process and is completely interchangeable with the COM model. So it's really an extension of the COM model. We don't think COM is going to go away anytime soon. We expect COM to be around for a long, long time. We continue to build COM things internally today. Really the benefit for a lot of what we're talking about here is benefit for the developer. And so if you're building something new from scratch, it would be to your advantage to build it using the .NET runtime as opposed to...
Is there anything that we would have to build with COM?
Is there anything that you would have to build with COM? Not that I'm aware of. There's no limitations of the runtime that would force you to have to build something with COM.
So COM Plus will manage object pooling and all that other jazz the same way with .NET components as it does with COM components?
We'll do that through interoperability. So we'll use the transaction services that are available on COM Plus and be able to support transactions within .NET components through interoperability. So you will be able to have managed objects that support transactions and all the other services that COM Plus provides. Okay.
Thank you.
Yeah.
Hi. For the .NET components, how's concurrency managed? I didn't hear any mention of apartment models.
Yeah, so we've basically done away with the notion of apartments where the runtime will manage and where you would have objects that live within a particular apartment and we would control synchronization. Instead, we've provided synchronization mechanisms that you could use as a developer, so you can synchronize access to a particular method or use synchronization objects within your code to control synchronization. The threads within the runtime are all are not initialized for any particular apartment style. If you want to use COM components, you can initialize them as apartment threads before you use those objects. But in general, we've left it up to the developer and to other frameworks to provide synchronization mechanisms.
Okay, so in VB, for example, if you have a .NET component built in VB and you are using it, say, from Visual C++, and you create an instance of the .NET object and you pass a reference of it, so now you've got two threads accessing that object. It's the responsibility of the VB programmer to provide any synchronization support?
Yes.
Okay. Now, is there any way to mark .NET components as whether or not they're thread safe?
Not that I'm aware of. There may be something that I'm just not aware of. After we're done here, you can come up here, and there'll probably be some other people around that might be able to, might know something more about that.
Okay, thanks.
Yeah.
I'm intrigued by the inheritance, implementation inheritance that you mentioned. But some many years ago, there was always this problem in object-oriented development that if you extended the base class and in your derived class you use the same method B, let's say, then there was an issue whether you should call method B of the base class at all, whether you should call it at the beginning of your B method or at the end. Mm-hmm. How will you deal with that here? You don't have the source code.
Yeah. So that's an issue that a lot of people will be struggling with. The way we think of this is we're providing you this mechanism for using inheritance. It's not something that we want you to go out there and just go hog wild on using inheritance and building things that everybody can inherit from. There's certainly still very appropriate uses for interfaces. And when you're exposing things to the public like that, you want to seriously consider using interfaces as opposed to implementation inheritance for the same problems that you're talking about. Now that said, there are mechanisms that we've introduced that make that problem a little easier to deal with. Things like the versioning support that we've added. So you can say that I want to bind to that particular version of the base class, not just any old one that's laying around. So I can have two versions of A, for example, in the demo that I gave here, and my B can be written in such a way that it specifically binds to the version I want.
Thank you.
There's also other things introduced in the languages, and you should look at the C# references, how you have to explicitly make methods virtual and explicitly override methods. So you can't just go overriding things at will. They have to. The author of the base class has to explicitly make it virtual.
Okay. Thanks.
Yeah.
I noticed that you didn't mention DCOM support or remoting.
So the remoting mechanism that we have in the .NET framework is completely based on SOAP and the HTTP protocol. That's the mechanism that we will be advocating going forward. But at the same time, the channel that we use is completely replaceable. So you can use a DCOM channel if you want. It's up to you.
Thanks.
Yeah.
How is licensing handled? Like if I develop a third-party class library on this framework and I'd like to distribute it and allow only my licensed developers to instantiate the classes?
Yeah, that's one of the biggest work items that we have in between now and shipping is the whole licensing model. So I don't have any details on that, but that will be a big chunk of the work that we're doing between now and shipping. So we definitely will have a licensing model. Yeah.
So I don't want to beat a dead horse on the ILDASM obfuscation, but so say you're a commercial component developer and you have your component that you want to expose. You want people to be able to browse it in ILDASM. But you have a bunch of utility classes that you use internally that you really don't want to expose. Is there any way to do that? Just say private, or say nobody can inherit from these?
No, by looking at them, nobody can inherit from it, did you say?
Yeah,
you certainly can make a type sealed.
Okay. But I mean,
make it so nobody can use it. But if you're asking, can you make it so nobody can see it in the metadata? The answer today is no.
So every class
again, we're working on.
Okay, thanks.
We're working on a mechanism to make that possible, so that you can basically, just obfuscate the metadata that's out there, so you can't look at it. Yeah.
Heard in an earlier talk that the assemblies will contain a public key and a signature, but not an entire certificate. How do you trust the public key if it's not in the certificate?
I really can't comment on the security issues. The extent of my knowledge is that the public key is used to uniquely identify the assembly. The point that I'm trying to make in this talk here is that the combination of the public key in the assembly and the type name is unique in much the same way that a GUID is unique in COM. And so by using those public keys and the type name, we can uniquely identify types. For the actual details on the signature stuff, you should go to one of the security talks that are being held tomorrow. Yeah.
Going back to remoting, in a scenario where you're trying to accomplish remote agent deployment, how would the .NET either accomplish or simplify that? Right now you have to make a lot of decom calls between the server and the target system to grab interfaces.
So we simplify it by actually fabricating those proxies, the proxy and the stub for you out of the metadata. We serialize the objects automatically and can actually remote the call, do all the proxy manipulation and everything on your behalf. So there's another talk tomorrow on remoting as well that you can probably get more details. But I can tell you that by looking at the metadata, we're able to synthesize the proxy and stub. And by looking at the metadata as well, we're able to serialize objects so that they can be transferred over to wire for a remote call. We can actually remote objects that way.
Okay, thanks.
Yeah?
I have a question about the runtime binding.
Okay.
Suppose I have a class with two methods called X, one with, let's say, a parameter of type object, and one with a parameter of, let's say, type datetime. And it's called by with a parameter of type object, which actually contains datetime. Which method is called?
A datetime is an object, so as an object of a specific type. So
But
you're saying if you have an object that contains a datetime, then it is a datetime. If you pass that datetime as an object, then it's going to call the object method.
If I pass the datetime as an object and I have two overloaded methods, one of them takes an object as a parameter, one of them takes a datetime as a parameter. If you do bind runtime, you can look at the runtime type which is passed.
Yeah. Again, it depends. My understanding is it depends on how you pass that object. If you actually do indeed pass the datetime object, then it would call the datetime method as opposed to the one that takes the argument of type object.
So you look at the compile time type of the parameters.
Maybe we should talk about it offline after, and maybe there'll be somebody else up here that may be able to clarify. As far as I know, it works the way I described.
Okay, thanks.
You might want to come up after though, and we can clarify. Yeah.
I've got a question about context and interception. Is there a similar mechanism in the .NET framework, like in COM+?
It's out of my area. I really can't comment on that. I'm not that familiar with those technologies.
Okay, just another question then.
Yeah.
Okay, retry. About SOAP. SOAP is the remoting protocol you just answered. How do you manage object references with SOAP and lifetime issues across the wire?
you should go to the remoting talk tomorrow, and that's a question that comes up quite often, and will probably be answered in that talk tomorrow. Why don't we take the rest of the questions offline and just come down here next to the stage. Thanks a lot.